Hi class, welcome to Refrigeration and Air Conditioning lecture number 5. Right, in this lecture, you'll be basically learning about psychrometrics at the same time learning about the CoolProp add-in for Microsoft Excel. Now, CoolProp is an open source free property database that includes a lot of pure fluids, pseudo pure fluids, and humid air properties. This is analogous to, or it's actually the open source version of the paid version, which is RefProp, which is widely used in the industry and academic work all over the world. And it's from NIST, the National Institute of Standards and Technology. CoolProp is the free version. There have been many studies which analyzed whether CoolProp database captures the same properties or with the same accuracy as RefProp, and it looks that they are very close. So the CoolProp, if you do a lot of calculations with CoolProp, it should be almost identical to the ones proposed by RefProp. So for this course, we'll be using the CoolProp database. Now it supports several platforms. It can be integrated with C and C++, Python, Modelica, LabVIEW, MATLAB, Ease, Octave, Microsoft Excel, etc. So in this case, we'll be using Microsoft Excel to integrate the CoolProp. And if you followed the installation procedure, you should have a Microsoft Excel file with working CoolProp formulas in it. And there are several formulas and functions, not several, let's say maybe 5 to 10 formulas and functions that CoolProp provides you. And the most important ones are the props SI and the HAP props SI that we will be using for psychrometrics. Okay, props SI is primarily used for thermodynamic property calculations of pure fluids, pseudo pure fluids, and humid air. And HAP props SI is primarily used for humid air, and sometimes you could achieve the same goal with using either of them, especially when it comes to humidity related problems. Okay, so at this point, what I would like you to do is try to open the test Excel file that gets automatically installed when you install CoolProp for Excel add-in. And you can see some sample calculations tab here. It shows a lot of sample calculations and it shows you the formula or the function that is used to do those calculations. Okay. One thing to note from the very beginning is all the units are in SI. Okay. So there's no place that actually tells you the exact units. When you put in a formula in Excel, you will have to assume it's in SI by default. There's no way to change the units, as far as I know. And you can see multiple functions being used here. There is a props 1 SI function where you're only using one argument or one input. Then there's the props function where typically you need 2 inputs, property inputs. And then there's the face SI function here, and then there's the humid air properties function here. Okay, all of those examples on how to use them in a formula, you can refer to this tab in the Excel file. And the actual formula is in this cell or in this column. Okay, all right, we'll come back to this. Let's start with some of the formula syntaxes of the main functions that we looked at. So let's start with the props SI function. So this is the syntax of this function. The first thing you need to know is what are you trying to get out of this function. So if you're trying to find a temperature, So you have to put in the symbol for temperature here, which is normally temperature is represented by a capital T. Okay. And then what are the input values you are going to give to estimating the temperature? For typical pure fluids, um, you need two independent variables or independent properties um, to determine the state of that fluid. So in this case, if you input pressure and quality, for example, and we'll get to quality later on, it's going to tell you about the temperature. Okay, so typically you need two inputs, and then you need to put in the actual value of the inputs, and then you have to tell the uh, CoolProp that what is the name of that fluid. In this case, we are trying to find the saturation temperature of water, so we put in a value of 0 for quality and a pressure of atmospheric pressure. This is in um, pascals, the unit. Um, and you get a value of 373, which is the 100 degrees C, right? So that's the saturation pressure of water at atmospheric conditions, which is basically the boiling temperature. Okay, so the two inputs and the value and the name of the fluid. Now, if you don't know the name of the fluid, or if you, for example, if you put water as not exactly caps in the first, sometimes it is caps sensitive. So um, make sure you have the name written correctly. And the way you can check whether you have the names written correctly is by going back to this Excel file, the test Excel, and go to the list, and you can see how the names of each fluid is written here so that there's no error. Okay, so if you make, for example, um, if you make a small error in the name, let me try putting this in small letters. See, the moment I change this name with a small r instead of the capital R, it gave me an error. So a lot of times um, there could be errors, and you can come back here to check how that name is written correctly. Now, sometimes you can use the same name that is listed here, or sometimes you could use the actual chemical formula of the substance. Um, so, for example, instead of the critical density of propane, let's look at the critical density of carbon dioxide. So I copied the exact name of carbon dioxide from the list, and I put it in here, and it seems to be giving me the correct value here. And this I could further change into actual formula and see whether that works. It works, okay? But a small error in the formula, if I change this to a small letter, for example, it creates an error. So it is case sensitive. So that's some basics about the props SI function. To actually see these particular calculations, you have to open the CoolProp functions Excel file that I had provided. You can go to the props SI tab um, and look at the saturation pressures of air and saturation temperature of air here. Okay. Um, so here, one thing to note here is the Q value, right? So the moment you specify an input of Q, which basically is called quality, you're by default telling CoolProp that I am on this line, which is the on a pressure versus temperature phase diagram. This side is liquid, this side is gas. and this line is the two-phase line or the saturation line. Okay, so basically you're both liquid and gas here in at equilibrium. Okay, at equilibrium. So when you specify a Q value, by default you're going to get, if you specify a temperature, you're going to get a pressure that corresponds to that. Okay, so it doesn't matter your Q value is 0, 0.1, 0.5, or any of those. If you specify a temperature, there's only one corresponding pressure, regardless of the quality. And by quality, what I mean is the amount of uh, liquid versus the amount of vapor, okay, in that mixture on that saturation point. If there is all liquid, then the quality is 0. If there is all gas, then the quality is 1, okay, or fully vapor. Okay, so it could take any value from 0 to 1. All right, so to prove this, let's try running this calculation, and you can see um, this is where the calculation is run, and this is the formula we're using. So if I change this value from 0 to 1 or any other value, you'll still get the same temperature because it's only dependent on the pressure on that curve. So for example, let's change the Q value. It's 0.5 here. I will change this to 1. So 1 gives the same value. Now let's change this to 0.2. Okay, it's the same value. So regardless of what you put in there, you will get that same value because you're on the saturation curve. Now this goes for calculating pressure using temperature too. Okay, so you can try any value from 0 to 1, you'll get the corresponding saturation pressure. Now, saturation pressure and temperature, T and P, are not the only parameters um, that could be calculated using CoolProp. You could calculate other properties like density, enthalpy, entropy, internal energy, specific heat, etc. So, what are the symbols used for these properties? In this Excel file, if you scroll to the right, you can see the common symbols that will work for each of those properties that we just mentioned, and the SI units in which the results will be um, generated by CoolProp. Okay, and one thing to note here is, of course, that the quality doesn't have any dimension because it's just the quality of vapor in the mixture. So it's almost like a mass fraction of vapor in a mixture. Okay, all right, and you can see specifically how um, each of these properties are calculated from these formulas here. Okay. Now, one thing to note here is not all properties can be calculated directly. For example, there's no way to calculate the specific volume directly using a formula. Instead, you'll have to calculate the density, D here, um, and then take the inverse to calculate the um, specific volume. So specific volume is basically the inverse of density. And there are some um, things to watch out for that depending on the function that you use. In this case, we are using props SI. Okay, everything in the in this tab is a props SI function. But when you use have props SI, which I will show you in a little bit, some of these symbols have a different meaning. Okay, for example, this D here could mean dew point when you're using the humid air function. Okay, so watch out for those kind of confusing things, and that can create error. Also, in this Excel file, you could see how to calculate some information that are specific to a molecule. For example, the molecular weight. In this case, the formula to be used is M. You can see M, and you don't need to specify any particular property because the molecular weight is independent of the properties, but you do need a placeholder for the property locations, and you can put 0 as the property. Okay, so you can change the name um, um, of the particular um, gas or fluid, and then you figure out what the molecular weight is. In this case, it's trying to figure out the molecular weight of these chemicals, um, and the value is usually given in kilograms per mole. You want to convert that to grams per mole for typical molecular weight measurements. So multiply this with 1,000. So the formula is in here. This is the formula that these cells are using, and this can give you a quick way to find out the molecular weight of any chemical that is available in CoolProp. More details on the same can be found in this slide. Now let's look into the HAP props SI function. Um, so in this case, there are 3 input properties that are needed compared to the 2 that are needed for the props SI function. That's primarily because this is a mixture of air and water vapor. Okay, so all the properties that the HAP props SI function is providing you um, is primarily of a gaseous mixture of air molecules and water vapor molecules. Okay, just assume these cross are water vapor molecules. Now, to determine properties, for example, pressure, temperature, um, density, etc., of the mixture, you need to provide 3 properties. One property that you can see in these formulas that is staying constant in almost all of these formulas that are shown here is the pressure P, which is the total pressure. Okay, and typically in most scenarios where we're considering ambient air or air in a room, the total pressure is very close to the atmospheric pressure, um, and it's around this value at sea level. Okay, now if you're considering the pressure inside a compressed tube with air or a compressed chamber with air inside, so you'll have to then use a higher pressure than this, so much greater the pressure than this. This could be 1 or 2 or 10 times the atmospheric pressure. Okay. On the other hand, if you're on top of a mountain or at a high altitude condition where the pressure is much lower than the sea level pressure, in that case you will use a value much lower than this. But in most scenarios that you're talking about, uh, like conditions inside or outside the room, you're talking about very close to this total pressure. So effectively, you're only inputting 2 input values. In this case, you can see the 2 other input values are temperature and the relative humidity. And we'll look in more detail with the syntax of this when we look into the actual Excel file. But just overall, you need 3 properties, okay, and then those 3 input values. Okay, there is no need to input a fluid name, okay, because it's by default for air and water vapor. So there's no name function or no name input in these um, formula. Now let's look at some examples from the um, Excel file. So you go to the HAB props SI tab, you can see several functions, several parameters being calculated using several combination of properties. Okay, So there's a dry bulb temperature being calculated using different ways. The output value is in Kelvin units. Um, there are different combination of input properties. Okay. Um, so if you look at what are the properties that you could be inputting in this um, half-prop psi function, it's the temperature, dew point temperature, wet bulb temperature, relative humidity, humidity ratio. Density is missing here. Okay. Instead of density, you have specific volume. Okay. And density, typically like the D value, which is used in props SI, is actually the dew point. And the dew point can be represented by either D or TdP. Okay. And by default, the temperature means dry bulb temperature, and it can be represented by T or TdB. All of those values would be in Kelvin units. Okay. Relative humidity can be represented by R or RH, capital R or RH. Humidity ratio using these two symbols. Okay. Enthalpy is H, entropy is S. So this is confusing. Specific volume is in uh, VHA and VDA, and how you calculate density is by taking 1 over the specific volume value. Okay, so you calculate specific volume directly and calculate the density indirectly. Um, and VHA is specific volume of humid air. VDA is specific volume of dry air. You could also use V for specific volume of dry air. Okay, whenever you have confusion, come back to this uh, Excel file and you can check what exactly is the variable name or the parameter name. Um, and P is typically the air pressure or the total pressure. Okay, total pressure. And P underscore W is the partial pressure of water vapor or pressure of the water vapor. Okay, so again, don't forget this particular note that I put in here. You have to calculate specific volume and take the inverse for density. Okay, now let's look at some of the calculations. Dry bulb temperature is the property that you want to calculate. Your input properties are pressure and humidity. Sorry, pressure, humidity, and wet bulb temperature. So you have a wet bulb temperature, you input the value in Kelvin, 284, and then your relative humidity is 50%, and your pressure, of course, is the total pressure of the mixture, which is the ambient pressure. In that case, this is the output value, 289.559. Okay, so I'll do something here. I'll try to put this as 1. Okay, and then we'll see what happens to the outlet value. What I'm expecting to see is at 100% humidity, wet bulb temperature and dry bulb temperature are the same. So I expect to see an output value which is exactly 284. Let's see. So that is correct. So if you change the humidity to 100%, you're getting the same value of wet bulb and dry bulb. And here you can see you're changing the inputs. Instead of the humidity, now you change this to humidity ratio, which is a ratio value. In this particular case, it's the kilograms per kilograms of um, moisture over dry air. Okay, so you could use those two inputs to calculate the corresponding dry bulb temperature. You could also use wet bulb and dew point to calculate. You could also use the partial pressure of water and the humidity, relative humidity, to calculate the dry bulb. So look through all these calculations. Different properties are calculated using different combinations of input properties. Okay, um, and I've tried to match all of them to get the same output results. Um, so you know that all of those properties represents the same state. So there are several ways to calculate relative humidity also. Um, again with different input combinations, humidity ratio, density. So density here, like I mentioned, you have to do 1 divided by the specific volume calculation, okay? Okay, so now let's try changing the humidity and see the effect on density here. Um, for now, let's keep the dry bulb temperature the same and just change the relative humidity. So this for the same temperature of the ambient, if the humidity increases or decreases, what happens to the air? So if I decrease it to almost 10% humidity, you can see that when humidity decreases, density increases. And if I increase the humidity to almost 100%, then you should have the lowest density. So it decreased to a lower value, okay? So that's how humidity affects the density of the mixture. You can also calculate the partial pressure of water vapor using the P underscore W parameter. So that will be the Pascal's value, how much the pressure of water vapor is in the mixture. The remaining pressure is air pressure. So if your total pressure is 101325 and the partial pressure of water vapor inside that is this, then um, the remaining is of the dry air, okay? The remaining pressure. And if you want to see the saturation pressure of water vapor under that same condition, what you will have to do is keep all the other variables the same and just change this to 100%. Okay, so that's the um, total pressure of water vapor. Sorry, the saturation pressure of water vapor in that mixture because I changed the mixture to be 100% water vapor. So it's fully water vapor. Okay, all right. I'll change it back to 50%. So you could actually see that when I changed that pressure, sorry, the relative humidity from 0.5 to 1, the pressure almost doubled. Okay, so as we have learned in the last class, humidity percentage is actually a ratio of pressure, the actual partial pressure of water vapor in air, to its saturation. That's exactly what you just saw here. Okay, so look through other examples. Depending on the homework and assignments, you might have to come back here and look at how things are calculated using some of the example formulas here. Okay, all right. So that was all about HAP props SI, humidity air props SI, syntax and its usage. Um, the last one is the phase SI. It's not a highly used um, function, but it's used for you to do a check. So if you are doing a lot of calculation in Excel and you want to check what state the phase is in, whether it's a liquid, gas, or two-phase, um, you want to use this phase SI syntax, okay? So if you go back to the Excel file, this is an example of usage of phase SI. And you can see the formula that's used here. And this one was primarily used for water, for example. And for different combination of temperature, pressure, quality, density, etc., this is trying to calculate what is the phase. So the only phases that are possible are liquid, gas, two-phase, whether it's a supercritical gas or not. It will not tell you whether this is a solid phase material or not. So CoolProp is not designed for solid phase, okay? So these are the phases that it can operate on. All right. And if you look at the syntax, it's pretty simple. It has two input properties for simple fluids, and then the name of the fluid, okay, and then the values for each of those properties. And then you have to specify the output um, uh, sorry, You don't have to specify any output. You just have to specify the name of the fluid. Okay. Yeah, output is basically the phase of the material. All right. Now that we talked about some of the CoolProp functions, let's try to calculate some of the humidity related parameters using CoolProp functions. Okay. The first one is calculating humidity ratio or specific humidity. If you remember the last class, we have defined what humidity ratio is. It is the ratio of mass of water vapor per unit mass of dry air. Okay, so basically this is the definition. Now, how do we calculate this? If you further remember from the last class, we are going to use ideal gas behavior for estimating humidity ratio. So for estimating the mass of water and mass of dry air, we could use the ideal gas relationship, which is here. Okay, you can assume that in that mixture, the water vapor behaves like an ideal gas, and the um, dry air also behaves like an ideal gas individually. Okay, and what is this equation? It comes from the ideal gas equation, PV equal to nRT. N you can split as mass divided by molecular weight. That gives you the number of moles, right? So if you can rearrange this equation into this, and that's what we are using here. So you replace the M water vapor with the PMV by RT of water vapor, so you get that term on the top, and the same thing for dry air. Eventually it becomes an equation like this because the total volume is the same, total RT is the same, RT constants are the same, and then it's only a ratio of partial pressure of water vapor and air, and also the molecular weights. If you choose to find the molecular weights using the phase SI, you can quickly figure out that, um, using the props SI, you can quickly figure out that the molecular weight of air is 28.96 and for water is close to 18. You put in that ratio here, and then you know the pressure of dry air using the ideal gas Dalton's law of partial pressures. We know that P dry air plus P water vapor is P total. Okay, total pressure is sum of these partial pressures. So you can rearrange everything and rewrite everything in terms of partial pressure of water vapor. Okay, so then you can calculate humidity ratio using this just simple formula. Okay, so let's see how it's done using the humidity calculator um, tab. Now, before we get to humidity ratio, uh, where we use this formula, I wanted to show you how to calculate partial pressure. It's already defined in the other Excel file, but let's go step by step here. So if you have a given dry bulb temperature and a given relative humidity, okay, and a given total pressure, then the saturation pressure is calculated using this um, props SI function. Okay. In here, you can see I have selected a quality of 1. I could choose a quality of 0.5, 0.2, any of those. It's going to calculate on that saturation curve. So if you give the temperature and uh, a Q value, it'll give you the corresponding saturation pressure. Now, if you have the saturation pressure, the actual vapor pressure is just relative humidity times that value. Okay, so just this two. So if I have 50% humidity, it'll be half the saturation pressure. Okay, you could do the saturation pressure calculation using the HAP props SI function too, which I've shown on the right side. So here, what you do is, and you can see there is a small difference. Okay, there's a small error with calculating with this versus calculating with this, and I've calculated the error percentage here. That's an inbuilt error within CoolProp. Um, and let's see. So calculating the saturation pressure. So first you use you're trying to calculate the partial pressure of water vapor and temperature for a given temperature, and you said humidity is 100%. So when 100% humidity with a ambient pressure of this, you're getting a saturation pressure value of this. You can also calculate the pressure water vapor directly using this by just putting in the humidity value of 50%. Okay. You could, instead of directly, so right now this calculation is not using this value. Okay. You could also just use this formula where you use this and times 50%. Okay. That's exactly what this formula is doing, but you don't really need to calculate this. You can directly calculate the partial pressure using one step. That's the benefit of water, the HAPS props SI. Here you had to do two steps. You have to first calculate the saturation pressure and then the partial pressure. Here you can calculate in one step. Okay, you don't necessarily need to calculate this, but there is a small difference between those two. Um, Probably some problem with their correlations they're using, but for the purpose of this course, that is very negligible. Okay, all right. Um, Now, if you know how to calculate the vapor pressure, we can quickly jump into calculating the humidity ratio. So if you know the dry bulb temperature, relative humidity, and the total pressure, what you need to know is then the partial pressure of water vapor. So if you know the partial pressure of water vapor, you use this formula, and that will give you the humidity ratio. Okay. So based on that formula, 0.621 times, using the atmospheric pressure and the actual vapor pressure of water vapor, you get a value of 76.646. You can do all that in one step using the HAPROPS SI function, um, where you specify the output as W, which is the humidity ratio. Okay. And your input parameters are these three parameters: dry bulb temperature, relative humidity, and atmospheric pressure. In one formula, you get the value. Okay. And you can see that I am multiplying 1,000 here because the output is actually in kilograms per kilogram. But typically, uh, even though that's the SI formula, typically um, when you talk about humidity ratio, that will be a really small fraction. So people normally refer to them in the grams per kilogram units, which is not SI. So I had to convert the SI units to this unit by multiplying with 1,000. Okay. So the error is roughly 0.6%. So, so now we know about calculating humidity ratio or specific humidity. All right. So now let's calculate moisture density, which is another humid air property or a psychrometric property. In this case, also, the primary estimation method is based on the ideal gas behavior. All right, so before we proceed with the derivation and calculate using the props SI and the HAP props SI, let's consider these four chambers. Now, this is the condition that we want to calculate the moisture density for. So it's a chamber with both um, air and water molecules or water vapor molecules. Okay, so that is at a particular total pressure, volume, and temperature. Now consider an equivalent dry air chamber. Okay, this is a dry air chamber at the same pressure, same volume, and same temperature. Okay, if that's the case, based on the ideal gas law, the number of molecules of dry air in this chamber will be exactly same as the number of molecules of moist air. And the number of molecules of moisture is basically number of air molecules here plus the number of water molecules here. All right. Now consider two other chambers with same volume and temperature. Okay. Now in this chamber, in the first chamber, you've extracted all the air molecules here and put them in here. Okay. And if that's the case, you'll get a particular pressure here, which will be much lower than the total pressure. And that pressure, you can call it the air pressure, but it's basically the total pressure minus the partial pressure of water vapor. Okay. If water vapor was in here, then it'll cancel this out and it will be total pressure. And the last chamber is only water molecules, and the pressure is basically pressure of water vapor. Okay. So now consider the molecules, total number of molecules in each of these chambers. Based on that, we have this first equation. Number of molecules of dry air is equal to number of molecules of moisture in this chamber, which is equal to individual number of molecules of air and water vapor. Okay. Now you rewrite them using the mass over molecular weight formula, because number of moles is mass in grams divided by the molecular weight in grams. And you can use that to derive this relationship. You can further rewrite that by taking out the molecular weight and multiplying it on the other side. So you get this equation. Okay. Further, you can rewrite this by taking out the molecular weight of air outside the brackets, and rewriting this way, where W is the humidity ratio um, that we just calculated, and it's nothing but m water divided by m air. So mass of water in this chamber divided by the mass of air in this chamber. Okay, which can be further rewritten in terms of um, mass of air related to mass of dry air. So we're basically relating the mass of air to the total mass of dry air here, based on the knowledge we have about the humidity ratio and also the molecular weights of air and water vapor. So if we know the humidity ratio in this chamber, um, then we can estimate the the mass of air in this chamber, provided we know the mass of air in a similar chamber, okay, where there's no humidity. Okay, now what exactly is density of humid air? It is written as total mass inside this chamber, which is m air plus m water vapor divided by the total volume. So that can be rewritten as this by taking out um, the mass of air and multiplying it with the humidity ratio. Okay. Now you replace this m air with this equation here. If you replace that, the rho of moisture can be rewritten mainly in terms of this equation, which basically you need to know the density of dry air, equivalent dry air, okay? And you also need to know the molecular weights and the humidity ratio of this chamber, okay? So in the previous calculation, we know how to calculate humidity ratio if you know the total pressure, if you know the relative humidity, and the dry bulb temperature, right? So once you know that, you can calculate this. And once you know this, you can also calculate, once you know the temperature of dry bulb, you can calculate the density of dry air. Okay, so using those two things, using the same three things, you can estimate the density of moisture. So let's use the Excel file and go to the density of moist air tab. Okay, and here you have two ways of calculating again, using the props.si function or using the hap_props.si function. Okay, using the props.si function, we'll use this formula that we just derived. And first thing is calculating the humidity ratio. And you calculate humidity ratio just like we did in the previous step by calculating the saturation pressure, then calculating the actual pressure, and then using the humidity ratio equation using the partial pressure of water vapor. Okay, so you calculate that humidity ratio, and then once you know the W, you need to use the density of dry air, which is easy to calculate. You calculate using air as the fluid and provide the temperature, which is basically 39 degrees C. Oh, one thing I forgot to mention here is you can do unit conversion inside. It uses Kelvin, so the 39 degrees C you can add 273.15 inside the formula, and that way you're using kelvins inside the formula. Okay. Um, Now, density of moisture, use this equation using W, density of dry air, and the molecular weights of air and water vapor, um, and you'll get this particular value. To check what happens when the humidity increases, um, it looks like when humidity increases, density of moisture decreases significantly, and when humidity decreases, density increases significantly, just as it should, um, as as what you have discussed before in the class. Now, it's interesting that the have props SI function makes this so simple because it's particularly meant for humid air properties. All you need is these three inputs. You don't need to calculate anything in between. In one step, it will help you calculate the density of moisture. So the first thing it calculates here is the specific volume of moisture, which is meter cube per kilogram. You just do a 1 divided by that value to get the density, okay, in kilogram per meter cube. And the difference between these two numbers is not that significant. It's very small error. Now the next parameter is the absolute humidity. Absolute humidity is also a parameter that's primarily estimated based on ideal gas behavior. Okay, so the formula to estimate that is this. Let's try to derive that. So absolute humidity is basically the m water divided by the total volume. Okay, so mass of water that is there in a total volume of the chamber. Now, now let's see whether this formula can get us to this value. So rho of moisture is nothing but m air plus m water vapor. I'll just write m water for now, divided by total volume. Okay, and W is m water divided by m air. So if you write this equation um, as it is, what you will be basically getting is 1 over W, which is m air divided by m water plus 1 times moisture, the rho of moisture. It's equal to m water, okay, um, divided by m air plus m water times density of moisture, which I have written here as m air plus m water divided by volume. Okay, so this will cancel. This is m water by volume, which is how we defined density, or absolute humidity. Okay, basically mass of water vapor in a given volume of that particular um, gas mixture. So this formula is correct as we verified here, and we have just derived density of moisture in the previous slide. So we can use that formula that we derived here into this equation, and we'll get this new equation, um, which we can further simplify like this. Okay, so once you know the um, the dry air density and the humidity ratio, then um, it's easy to calculate the absolute humidity. So again, we only need the dry bulb temperature, relative humidity, and the total pressure to calculate the density of raw air and also W. And all of these values can be calculated based off of that. So let's look at the Excel file. Go to the absolute RH tab, and here you have the dry bulbs, relative humidity, and the atmospheric pressure. The first thing you calculate again is saturation pressure, and then the actual pressure. Then find the humidity ratio W based off of that, like we did before. Then calculate the dry air density. Use the dry air density and all these values to calculate the moist air density, like we did before. And then use the formula that's shown here to calculate the absolute humidity. And the value here is basically multiplied by 1,000 to get the value in grams instead of kilograms, okay? Um, so that's 5.61. You could do that as a one-step calculation here. Um, Sorry, even in HAP props aside, it's not a one-step calculation. It's a multi-step calculation. Here, what they do is calculate um, the humidity ratio, then calculate the dry air density, then calculate the moist air density, and then use this formula here. Okay, so it's actually a three-step process here. I forgot to mention that there is no absolute humidity function in HAPROP SI. Okay, so you have to indirectly calculate this way. And the error calculated is also not very low, but it's reasonably low enough of 0.425%, okay, compared to this value here. So what happens when relative humidity increases? When relative humidity increases, absolute humidity also increase, okay? And it decreases when absolute humidity also decrease. All right. All right, so now let's think about calculating the dew point temperature. So what exactly is dew point temperature? As we had discussed before, so let's say there's a mixture of air and water vapor. Okay, so the X here is the water vapor. Now it's at a particular dry bulb condition, T dry bulb, and also a particular total pressure, P total pressure. Okay, now assume that the water vapor is at a pressure P vapor. Okay, how do we find the dew point or the point where it will start condensing? What we have to do is assume a chamber, okay, and it has only water, okay, only water, same pressure as this here, okay, same pressure, there's no air. Now it has some particular temperature, okay. Now if you keep dropping this temperature, at some point there will be some liquid, okay. And when you have a liquid and liquid and vapor in equilibrium, that condition is saturation condition. So at that point, this temperature is T saturation. So we have to find a pressure based on the partial pressure here on the saturation curve. Now, you cannot measure just the pressure of water vapor using a sensor. So what do? we can measure the total temperature, which is the dry bulb. We can also measure the relative humidity using a relative humidity sensor, right? So if you know those two things, you can calculate the partial pressure, sorry, saturation pressure of um, of TdB. Okay, what is the saturation pressure at dry bulb condition? So that you can use the again the saturation curve and calculate this pressure. And if you know the relative humidity using your relative humidity sensor, you multiply that saturation pressure at dry bulb with the relative humidity value to get the P vapor. Okay, that will be the actual pressure of water vapor here. All right, so that is by definition of relative humidity. Okay, now you want to know the corresponding saturation temperature at this P vapor. So you find this value first, multiply with RH%, and then you'll get a smaller value, okay? And that value is the actual pressure of water vapor in the chamber, and find the corresponding temperature on this plot at saturation. That is the dew point, okay? Now, if the humidity is 100%, then these two lines will be exactly the same. So dry bulb will be same as wet bulb, and dry bulb will be same as the dew point, okay? So this is the method, 2 steps, if you're using um, the props SI. Let's calculate that with the Excel file. All right, so dew point, you have dry bulb, relative humidity, and atmospheric pressure. You calculate the saturation at dry bulb, which is 29.7 is what I've given here. And the actual pressure will be just multiplying this with relative humidity. And once you know that, you can calculate dew point using the saturation function again. So in this case, you want to find the saturation temperature for the new pressure, which is the actual vapor pressure. And again, you can choose any Q value. You can put 0, 0.5, 0.1, any value here, okay? Um, and then you get the value in Kelvin. So you can do a subtraction of 273.15 to get the value in degrees C, okay? With have props SI, it's much easier. It will just directly put in the TDP as your output. You give it the dry bulb and the um, relative humidity and the total pressure. It'll automatically give you the value. And the error is not much different between the two functions. Okay, so that's the dew point. The next item is the wet bulb temperature. Okay, here it's a little bit more tricky. In this case, a heat balance or energy balance is required to balance out between the sensible cooling of air with the latent heat of evaporation of water. So if you remember in the class, we had talked about the sling psychrometer where the water evaporates and reaches a really cold temperature where it stabilizes and then it doesn't evaporate any further. All right, so what happens is the latent heat of cooling, latent heat of evaporation matches the sensible cooling, and at some point there is no further evaporation. Okay, um, so how do we calculate that? So let's consider a small um, amount of water that is on the thermocouple that's evaporating, okay? And let's say the amount that evaporated is M water, okay? That's the small amount of water that has evaporated. And while it's evaporating, it takes Q from the surrounding air, okay? Small amount of Q. That drops the temperature of the surrounding air from, let's say, the dry bulb value to the wet bulb value. Okay, so there's a small temperature change from the air because the water is evaporating. If you did an energy balance, the latent heat of evaporation is the amount of water that is evaporating times the latent heat of um, evaporation. So that's the total heat of evaporation. And the amount of energy that's removed from the air is total amount of air that's around that water from which this heat is removed times the CP, which is the specific heat of air, times the temperature difference. Okay, so that's the energy balance. We are equating this to this. Now, how do we calculate the amount of water that is changed? So what we do is we consider the W of the air before evaporation, W1, and after evaporation, like specific humidity before and after. Okay, so that change in W times the mass of air, because mass of air is same. Okay, mass of water is what is changing. So mass of air times delta W will give you the total mass of air, water that has evaporated. And delta W can be identified or can be calculated based on this equation. One, you calculate the W at saturation, assuming it's saturated at the low temperature, because when the wet bulb temperature is reached, the assumption is that the mixture is saturated. Now, when the dry bulb temperature is reached, whatever humidity ratio that you will calculate, that is the initial humidity ratio. So um, that difference will give you the delta W, and that could be used in this equation for energy balance. So this is the overall energy balance equation um, that we will calculate using the props SI function. However, you can notice that the wet bulb value is not an explicit function here. It's present on the left side and inside the saturation humidity ratio function also. So it's an implicit function. Okay, so it's not easy to estimate wet bulb temperature by just doing a basic calculation. So you'll have to do some kind of iterative solution um, or a solver-based solution in Excel because it's an implicit function. Okay. All right. So let's go back and look at the Excel file. Um, all right. So go to the wet bulb temperature calculation tab, and you can see um, to do this energy balance, you have to estimate the left side and the right side of that equation, and both sides involves using a estimated or initial wet bulb value, and then the energy balance is trying to optimize or minimize the error between the left-hand side and the right-hand side of the equation. Okay, so the left-hand side is this, and the right-hand side is basically the heat of fusion times the delta W. Um, the heat of evaporation, sorry, latent heat of vaporization. So all of that you can see here how those things are calculated. So enthalpy of liquid is here and enthalpy of vapor is here, and the difference is uh, the latent heat of vaporization. Okay, so go through all these formula, how that is calculated, um, and you can see how um, the total energy is estimated on either case. And if I change the wet bulb initial gas to some other value, you'll see that the energy balance is not there anymore. Okay, there's no zero value here. So, so again, you hit the solve button. I guess the macro is disabled. So it didn't work because the macro was disabled, and I've closed and opened the file again, and it'll give you this warning if you have the macro settings right. Then enable the content, and now try to solve it to make sure that the absolute value here is minimized. Click OK. So it seems to have minimized to a little bit. So the value we got is 17.142. It's close to the earlier value. Um, let's change the humidity value here and the temperature, and you can see the absolute value is not minimized. Solve again, so you get a different number, 21.95. Um, is the wet bulb temperature if you have 30 and 50% humidity. So now let's try to take it to close to 100%. Let's see 100% whether it will give you an error or not. At 100%, I'm expecting the wet bulb temperature calculation to get you same number as 30 here. So yeah, at 100% humidity, the dry bulb and wet bulb temperatures are the same. Okay. Now, the value here, which is calculated using HapProps SI, it directly does all this optimization and everything for you. Okay. Um, so you don't really need to run the solver for calculating using HapProps SI. Only if you're using the actual thermodynamic principles and using step-by-step calculations of energy balance, you need to use the iterative method. But you can get all that in one click, in one line, using the HapProps SI method. Okay, so let's do one more. 70% humidity. So it's predicting 25.502. Let's try the solver and see what this value is, 25.466. That's a 0.144% error. So it's a small error in the calculation based on these two methods. So now we have found um, or explored different ways to calculate various humidity parameters. Um, all of those parameters are combined together in here if you want everything in one place. Okay, so this should be more than enough for you for calculating the properties of um, any condition using psychrometrics. Another feature of this particular Excel file is that I've included the charts tab, which helps you um, understand the actual relationship between parameters um, by plotting them. Okay, so all of these are a one-off calculation of a single point each time. So here you can actually see the relationship between different parameters as they are varied. Okay, so this will further help you with the understanding of the physics behind psychrometrics. So, for example, here you can see humidity ratio on this axis is varied with relative humidity under various dry bulb conditions. Okay, so what happens when relative humidity increases? Of course, the humidity ratio, which is the mass of moisture divided by mass of air, of course increases. Now, what happens when the temperature also increases? Okay, so when the temperature increases, the rate of increase is even higher. Okay, so a lot of those relationships are plotted in here, and they're also presented in the lecture material. Okay, so you could use those to develop an understanding of how different parameters vary. So this is straightforward, um, and humidity ratio versus um, so the first one was absolute humidity as the humidity relative humidity increases, absolute humidity also increases. And as the temperature increases, the absolute humidity also increases. Same thing goes for humidity ratio. Um, and then we can look at the uh, water vapor pressure, the actual pressure of water vapor as the humidity increases for various dry bulb conditions. Of course, the values at 100% humidity, these all represent the saturation condition, right? So at each temperature, for example, in this case here is 10 degrees C, you have a particular pressure value here, right? So if you calculate or if you plot these values, you will see that those values lie exactly on the saturation curve at 100% humidity. All right, so that's what that is. Um, the next one is the density variation with relative humidity. As we discussed in the class, moist air is lighter than dry air. So this is dry air, 0% humidity, okay? And as the moisture increases with the relative humidity, the density decreases, okay? And the reduction of density is highest when the temperature is also highest. It seems like this drop at 30 degrees C seems to be a much bigger drop than the drop that happens at colder temperatures. Okay. Um, then this is the dew point versus relative humidity. Um, so let's say you have a particular dry bulb condition of 25 degrees C. Okay. So that would be this one. And at 100% humidity, the dew point is same as 25 degrees C. As the relative humidity keeps decreasing, the temperature at which condensation will start, which is the dew point, it will also keep decreasing. Okay, and at some point, um, you have reached almost the freezing point of water. Okay, at some particular relative humidity, your the dew point is almost same as the temperature of ice. Okay, you're almost directly becoming ice. All right, so that's the dew point relationship. And the next one is the wet bulb. Um, so the wet bulb is also a temperature that is lower than um, the dry bulb temperature. And as you can see, wet bulb also decreases as the relative humidity decreases. Okay. Now, how does the wet bulb and dew point look compared to each other? So you can do all these calculations in the Excel file, and all of these are in here. All of these charts are in here, and you can verify the calculations yourself. Okay. Um, all the plots that are listed in the coursework material are in here, and you can click on the chart and find where the data is coming from and verify the calculations. So as you can see here, wet bulb temperature and dew point temperatures are plotted for one particular dry bulb condition, 20 degrees C. When relative humidity is 100%, T wet bulb is same as the dew point. Okay, and after that, it seems like dew point is always lower than the T wet bulb. Okay, just remember that dew point is almost always lower than the wet bulb temperature per our calculation, and it only equals the wet bulb temperature equals the dry bulb temperature equals the dew point only at 100% humidity. Okay. All right. So with that, I think let's complete this lecture. And there's psychometrics doesn't stop here, but this is a good start. You should keep learning more to understand this better by um, tweaking that Excel file and doing more calculations with that Excel file. All right. Thank you.